Alright, so we're continuing on with the week 4, and here's an example. This comes from Dr. Selmer's notes. So we have a design. Our goal here is to design a shock absorber, which by design we were going to find out the specifications for the stiffness and the damping constant for a system with a mass of 450 kilograms. And so the period is 1 second. All right, so we're going to assume, well, it says tau d, so it is the damped period. And the displacement amplitude of 1/3 of its original value, right, for the first half cycle. All right, so let's see. So some of the idea here is, we're going to have this thing right here going, we expect. And so if it starts at the top, which is often the case, that's fine. Here is 1 full cycle, right, coming from here to there. So this is going to be the tau d. So 1 half cycle is going to be, I think, right down to there, right? Boom. And so that should be 1/2 of a second placed onto this. So first, let's see. I will find out. What do I want to do first? Okay. So what I can say, so from the logic of this, we are going to assume that if x1 over x1.5 is equal to 1/3. Therefore, we're going to also say that we're going to expect, if the ratio remains the same, that x 1.5 to x2 for the next half cycle is 1/3. So if we do that, we go basically that, therefore, x1 over x2 is going to be equal to 1/3 times 1/3, right? Because what you'd have is be able to cancel out if you multiply them, you'll cancel out the 1.5 right in there. So we expect that to be 1/9. And if that's the case, then we're going to have a log decrement of natural log of 1/9. And we looked at hit that in our calculator, and that's 2.197. Okay. All right. So from one of our main equations that we were using here, we can find out that the squiggle, if you want to use the funny version of the thing, the xi, I guess, the damping factor. We can just call it damping factor. We have 2 pi squared plus del squared. All right, and so we can go ahead. We have all the information we need. So 2.197 divided by 2 pi squared plus 2.197 squared. Put it down there, is equal to 0.3301. That's not a bad amount of damping. We want to come back to this graph right in there. So we're still kind of in this zone right here. So still kind of in the linear area, not quite enough for us to matter. But anyway, so we can now proceed with, we can find, should have been able to do this anyway, huh? Let me see. I guess we can get the natural frequency. Yeah, that's what we can do. So we can get the undamped natural frequency. So we should have been able to get the damped natural frequency. So I almost kind of want to check this other one out right here. We could get the damped natural frequency from this. I guess we don't need it. Either way, we could have gone either way. So we know that we can get, here's an equation for the period, the damped period. Oh yeah, this is actually Okay, so let me go back just 1 second and show you where that might have come from. We know that the definition of the damped natural frequency is the undamped natural frequency times 1 minus squiggle squared, the damping factor squared. So what we've just done over here is we've just divided by 2 pi and got the damped natural frequency, then we took 1 over it for the period. So now we can go work this equation backwards and get this one, the natural frequency, by replacing, just swapping these out, tau d and 1 minus squiggle squared. So we have 2 pi over 1 second times the square root of 1 minus our damping factor 0.3301 squared. And what we're end up with is 5.931 radians per second. Alright, so now that we have that and we know the mass, we can find out what the spring rate has to be. So because we're going to have natural frequency is equal to square root of k over m, therefore we can find k is going to be equal to, so multiplied, yes, natural frequency squared times the mass. So 5.931 squared times the mass, which we were given as 450. So we end up with 15,830. And if you look at the units right here, this would be kilograms, and inside here is a radian per second. So really we have kilograms per second squared, which doesn't make any damn sense. But if you recall, you can use the equation F equals ma, so that newtons equals kilogram meters per second squared. So if you get kilograms, you can have a kilogram is going to be equal to a newton second squared per meter, right? So if you replace that in there, back in there, you can see that we're going to get a newton per second squared per meter, so we have a newton per meter. So you can see that it is the same thing. Try it out yourself. Want to make those units balance out. So now with that, well, we don't need, this is part of our answer, right? So that is find k. So now we just need c. So we get the critical damping is going to be 2m omega n. So 2 times 450, maybe we'll put the kilograms back in there, times the 5.931 radians per second. And once again, we get the weird kilograms per second, but we could use the same idea as we had above over here to replace that, and we'll see that we will get the expected units, which are, first there's the number, there's the critical one. These are Newton meters per second. And so finally we'll get an answer here for the critical, which is going to be C is equal to the damping factor, critical damping factor times the critical right here. So we have 0.3301 times 5, is it 5 point? No, it's 5,000. It should be, hopefully that's a comma right in there. Yeah, that looks like a comma now. 5,338. So we're left with a factor or damping coefficient of 1,762 Newton meters per second. All right, so those are the answers. They don't quite match what Dr. Bob has in his notes, but I think I got it right. These should be the right values. If you find a mistake somewhere, please check me and let me know. We'll do some more examples.